Good morning, everyone, and welcome to the first session of MassMEP's Practical Guide to Additive Manufacturing webinar series. For those of you I haven't met, my name is Kevin Tata, and I'm the marketing coordinator at MassMEP, and we're really glad that you came with us to kick off this series. If you're already familiar with MassMEP, welcome back. And for those joining us for the first time, welcome to MassMEP or Massachusetts Manufacturing Extension Partnership. There's an MEP center in every state across the country, all working towards the same goal of supporting manufacturers and helping them grow and compete within the state. This series is being delivered in collaboration with MIT's Center for Advanced Production Technologies, and we're excited to bring that partnership to you. Before we get started, I'll cover a few housekeeping items. This session is being recorded, so if you need to revisit anything or share it with any colleagues, we will provide this afterwards, the recording afterwards, to some confirmation emails to each of you. We also encourage participation throughout. Feel free to use the chat, ask questions, and engage in the discussion. These sessions are always more valuable when they're shared dialogue. Um, if you feel you can put it in the chat or you can come off camera or on camera and raise your hand if you feel this is a small group. So we do want to promote that shared dialogue. I also want to briefly mention our survey process with MassMEP. MassMEP is a nonprofit supported by state and federal funding, and we report to NIST, the National Institute of Standards and Technologies, to understand the impact of programs like this. We will ask someone from your organization to complete a short survey in the following months to just go over the series impacts on your company. So now we can talk about why we're here. Additive manufacturing. Additive manufacturing has evolved significantly over the past few years. It's no longer just a prototyping tool. It's become a practical solution for improving lead times, enhancing design flexibility, and solving real production challenges. At the same time, many manufacturers are still trying to understand where it fits within their operations. And that's exactly why we're here and why we created this series, is to provide more clarity, not just what additive is, but where it makes sense, where it doesn't, and how it can be applied in real manufacturing environments. We're excited to have Hayden Quinlan and Mandy Moshiri from MIT APT leading this session. They bring a strong mix of industry experience, research, and practical applications. And we're looking forward to the insight that they'll share with you today and then the upcoming sessions. Like I said, this is a six-part session series. So you will be getting confirmation emails as we get closer to the upcoming dates. But other than that, we appreciate you taking the time to be here and invest in this learning opportunity. And with that, I'll hand it over to Hayden and Mandy.
Thank you. Thank you, Kevin, for getting us started, and
Absolutely.
thanks everyone for joining. I just want to repeat one thing that Kevin said. It's nice that we have a smaller group here today because it means we can be very intimate, friendly, and no one has to be shy. So if you have questions at any point, feel free to pause, like type them in the chat, raise your hand. I just want to reiterate that because we're happy to stop, answer those questions as we go. The whole purpose of this webinar and the subsequent webinars is to help. So sometimes at MIT, we give lectures where we talk at you for 45 minutes or so on. That's not what this is about. This is instead, as the session is titled, trying to be very practical and meet you where you're at and solve real problems and allow you to make use of additive manufacturing or 3D printing technology. So in keeping with that spirit, you'll get out what you put in. Hopefully we'll tell you stuff that's insightful anyways, but the more questions you ask, the better experience for everyone. So this session is broken up into roughly three parts. So I'll do a little bit of introductory material. We'll talk about how you get started with additive manufacturing, and then we'll wrap things up and talk about a few opportunities to further extend your learning beyond this webinar series itself. First things first, though, I do want to sort of just reiterate the purpose of the series and give you the dates as well for the upcoming sessions. The big thing, like the big takeaway, for this slide and kind of the topics and sessions that we put together, is it's really targeted to an SME audience, an audience that maybe doesn't know that much about additive or has tried it a little bit, but isn't quite sure where they want to go or how they can take advantage of the technology. And you'll see that the topics are really grounded. These are not like advanced research topics or emerging technologies or, nanoscale printing or some of the other things we think about. The real focus here is trying to identify and solve very practical challenges, opportunities that you may face. Everything from how do you design good printing applications, which is sort of the purpose of this webinar, to building a structured methodology for approaching them from material process selection, cost modeling, et cetera. That's sessions 2 and 3. And then sessions sort of 4 and 5 are really focused on like the nuts and bolts of just buying equipment and installing equipment and what does that look like at your organization? What do you have to manage there? We've bought a lot of tools at MIT. And we have quite a lot of tips and tricks to share with you about how you can do that efficiently, and maybe more importantly, how you can do that safely. Because depending on the process technology, things can get a little wonky. And then last but not least, we have our sort of regional resources program. That's where we'll talk about all the other ways that you can learn, stay up to date, engage with the really amazing additive community here in Massachusetts. And we're hoping to do that one live actually from Germany, where there's a large trade show called Formnext, the largest in the world for additive manufacturing, where we can both tell you a little bit about what's available in your backyard here in Massachusetts, but then also teleport you to Europe to share a little bit from the show floor. So, just quickly about myself, and I'll let Mandy introduce herself. I'm a senior program manager here at MIT. I've been doing additive for 10 years as of actually this month. So, my first day, well, was roughly March 1st, 2016. And throughout that time, all of it has been focused on workforce education, engaging with industry in collaboration with MIT, building new laboratories supported in part by the Center for Advanced Manufacturing in the Massachusetts state government, and then also doing some startup things on the side, also related to 3D printing. So I've seen it all in a way from a research point of view, a lab point of view, as well as through close work with industry. And then Mandy, feel free to introduce yourself.
Yeah, thank you. So I'm Mandana Mushiri, but just call me Mandy. Mandy, please. I have a bachelor and master in materials engineering from Italy. I've been specializing in metal additive manufacturing during my PhD and after. I've been working for more than 8 years at the Lega Group, where I was leading the research and development area on metal additive manufacturing materials and technologies. And I've joined MIT in last July. I'm working here with Hayden as research scientist.
And we're very happy to have you on the team, Mandy. So a little bit, well, now I'll sort of get into the heart of the webinar, and I'll just tell you a little bit more background about why we at MIT care about additive manufacturing, which is to say, in our history, we, not me specifically, the royal we of MIT contributed pretty considerably to its development. The first technology that was ever called 3D printing is a process that's now called binder jetting. That was invented here at MIT, and actually the professor on the patent, Emmanuel, or as we call him, Ellie Sachs, still works out of our machine shop every day. I see him all the time. So MIT has had a soft spot in its heart for 3D printing for a long time. And we sort of built on that by building new laboratory spaces and so on, trying to build programs that are meant to help not just our research community, but in fact the Massachusetts industrial base learn and adopt 3D printing technology. And so at several points, I'll make a plug for what we've got going on at MIT. I'll try not to do that very much, but this is one of them where I'll say that we have really, really amazing tool capabilities. We have polymer 3D printers, metal 3D printers, things that print at the nanoscale, things that print, walls of houses out of cement, and everything in between. And all of those tools are available for industry to come use and explore. There are different models depending on the building, depending on the tool. But the answer is always, if you are interested in accessing machine tool capability and you don't want to buy a machine, you can certainly reach out to us, and we'd be very happy to support your project, whether that's a prototyping application or a benchmarking application, sort of whatever it is. The only thing we don't do is production. We do all the R&D stuff, but we won't like, we're not a contract manufacturer. And if you're interested in what those tools look like, you can check out our website on the bottom, apt.mit.edu. And then last, by way of introduction, just to tell you a little bit about where the experience, where our experience comes from. We've been doing this a really long time. So we've been teaching additive for the last 10 years. We've done that in person. We've done that online. In 2018, we launched at that time, the world's leading online training course, trained over 10,000 people through that online mechanism. And now, especially since, say, 2021, 2022, have built out those laboratories that I just mentioned and done a lot of applied project work. So we have what I would say is a pretty, robust set of experiences in 3D printing technology. That said, I don't want to spend all this webinar talking about who we are and what we've done. The important thing is how do you get started with 3D printing technology? So I'm going to kick it over to Mandy, who's going to tell you about some basic things about the technology and then how you can start thinking about how this type of machine tool can add value in your organization.
Great. Thank you, Hayden. If you can change slide. Thank you. So when we want to get started with a new technology or with anything, it's great to start from the best is to start from the beginning, and the beginning is the definition. So here we have the ASTM standard definition for additive manufacturing, which is said to be a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. And it might sound simple, but in these 3 lines, we have all the main concepts, like it's all the main concepts that distinguish additive manufacturing from other technologies are within these 3 lines. And we can unpack it a bit further in the next slide by looking at the main process categories, manufacturing process categories we have. So first we have formative manufacturing processes where the part is shaped using pressure, using temperature, for example, a mold, like for injection molding, thermoforming, casting, where material is not really added or removed. Then we have subtractive technologies where, as the name says, you remove material, you subtract material. So like milling, turning, grinding, and so on. And then the category where we are focusing on, that's additive manufacturing, where you can selectively deposit material, you can join material. It's sort of development from the more old-fashioned welding process, but it's actually within the distinction in between subtractive and additive that additive also finds his own nature. So if we go to the next slide, thank you. We can see that subtractive technology is like building up your statue, starting from the block of marble and start removing material. While additive, it's building up your statue, for example, using Lego bricks. So you add a brick on top of brick to make the David. And the David is the name of this statue. It's not just how the part is manufactured, but it's also how the part will look like and how is the design mindset that you need to use in order to get to the final product. So we can also see that the picture on the left, the statue on the left, this is how you would design how you want to wish your statue to look like in the end. While the one on the right is what you might get after printing, before post-processing, because of the slicing procedures, because of the process itself, how it works. And we will talk more about the design mindset. We can now go to the next slide. Thank you. And we can start with how in general how additive manufacturing work, and there are many different types of additive manufacturing technologies. Each one use their own functioning principle, so they can work actually very different from each other. Here we will just present what's usually called powder bed fusion or selective laser sintering, which is one of the most widespread on an industrial level as a technology, where basically it works by spreading one layer of powder with a recorder. Then one or more lasers will start scanning and selectively melting areas of the powder bed in order to melt the material. The material will solidify and join within the layer, but also with the previous layers. And then the build plate will go down one step, a new layer of powder is spread, and the laser will start scanning again. And the process repeats itself until the full part is completed. And this technology can be used for metal, for polymer, like for many different types of materials. And we are very curious also to hear what you're investigating, also what you're curious or which technology you are using in your industry. So if you can share it in the chat box or later on after the presentation, we would be happy to hear. So if you go ahead one slide, thank you. Thanks. So if we take a look about implementing this technology within a full manufacturing process chain, so first of all, you start with the CAD design. So you prepare the design of your final product, then you upload it to what we can call a CAM software, which is actually a job preparation software, where you will add support structures, you will put the parts on the build plate, you will orient the part, you will slice the part since the printer will print it like layer upon layer. And then you actually convert the file format into something that the printer can read. So you upload the file in the end on the printer. Then on the printer, you will run some routine steps like adding the powder or aligning the laser. So all these following all the checklists before pressing start. And once you press start and the job is finished, of course, you will need to clean from the leftover powder, the final part. If you print it with metal, the parts will be actually welded on the build plate. So you will need to cut them off. Then depending on the material or the process you're using, you might need to do heat treatment or sintering. And also depending on the material, the geometry, you might also need to do some heat treatment before cutting. And then there will be, it can be quite an intense sequence of post-processing and surface finishing steps. And this is all to make sure that your final product has the wish dimensional tolerance, the wish surface finishing that you actually need in your final application. And last but not least, you will need a quality control step. And actually you can add quality control steps at every phase of the process chain. But this is going to be to be sure that what you have printed and post-processed is actually going to be functional in your final intended application. And if you go to the next slide, thank you. So usually when we prepare CAD design, when we prepare design for a product, we tend to think that in the design phase, or we can call it the CAD step, we just need to think about what's the part meant for, what's the final application. Maybe we would run some simulations to make sure we optimize the design for the application, but usually think that we just need to think about the final product, how it will look like the final Michelangelo's David. If you go to the next slide. Thank you. But in reality, the design phase is actually much more complex. At the design phase, you need to have a clear vision, not just of your final product, but also of every single steps of your manufacturing chain to make sure that what you're printing, what you want to manufacture, you can manufacture. Like it would not just work, but you can also manufacture it. So for example, you need to design something that it's printable. So something that has the right overhang angle, surface angle. If you want, you need to add support structures. You can actually access at the end the support structures in order to remove them. If you want to print, let's say, an enclosed shell, you will need to think about how you would powder it. So you need to add holes on your shell to make sure you can remove all the powder. If you need to sinter the parts, you need to make sure that you're designing something that doesn't have too many hollow or large hollow structures. Otherwise, during the sintering will collapse. If there are functional surfaces that need a specific roughness, need a specific dimensional tolerance, you need to make sure that all your cutting tools will have easy access to these areas, and everything is compatible with your fixturing systems. And again, also, we talked about having access with the cutting tools, but also with the probes if you want to measure it, like with a CMM. So the design phase at the CAD part is you need to have a full overview of the entire manufacturing chain. And if you go to the next slide. Thank you. So when you actually want to integrate a new technology, whatever is the technology, now we're talking about additive manufacturing, but if you want to integrate, let's say, an additive manufacturing technology within your factory, there will be no solo player. Like it's not a standalone technology. In order to make it work, you need to consider the full integration within your manufacturing line. So you need to have very clear what's your entire manufacturing line and what's the purpose of your application. Because if there is one instrument which is playing off, the director will actually hear it. The part will not end up being successful or as successful as you wish. And the integration should be both on a physical level, so what you print, you can mill, you can measure, but also on a digital level. So the file format involved in every steps are also covered, like what you are designing can be read by a CAM software, can be read by the printer, can be uploaded to a software for doing simulation to make sure that you don't have cutting tools collisions with your PLM or with your simulation software. So the integration just is not just on a physical part perspective, but also on a digital level. And if you go to the next slide, so we have talked about the factory level, we have talked about a bit of the design mindset, but what makes sense to print? Like now we can move our focus from the factory to the product itself. And there can be many reasons, for printing a component where additive manufacturing makes sense. Here we reported 6 that are among the most common and known reasons for which many industries has implemented additive manufacturing in their factory line. One of the most common one is actually what we call metamaterials, which is quite a fancy term just to say that you can print parts which are lighter but still having the same level of stiffness or mechanical resistance that you intend. And a very famous example is actually the Riddell helmet. So you can just print the material that is bearing a load. So the parts will end up being more light. Or you can use it for manufacturing flow heat exchangers because you can optimize, for example, the cooling channel design. Or a very famous example, especially for the aerospace application, is that with additive manufacturing, you can design new materials that can sustain extreme environments. So it's actually opening up also from a material design freedom. Mass customization, probably the most famous example here are the Invisalign retainer for the teeth, where they are basically with one manufacturing line, they are printing retainer, which are specifically for each patient. And this is all enabled thanks to digital manufacturing technologies. Then about rapid fulfillment, we talk about spare part, like keeping the production running when something breaks, and or also developing solutions to make some of the tasks within your factory line simpler or faster to execute. And last but not least is the assembly consolidation. GE actually provided a lot of good examples on why this is interesting. So, for example, for the propeller called T901, they have assembled 50 different parts into one. And the benefits of assembling to 50 parts into one is not just that we are not sure if the part was cheaper or more expensive, but on the entire supply chain level, there are 49 less parts to handle from a procurement perspective. When you want to do quality control, you need to do the quality control just on one part instead of 50. The risk of errors during assembly, also the cost of maintenance while checking 50 parts or just checking one. And it was also shared that the parts was not just lighter and from 50 being to one, but it was actually performing even better because they could optimize certain design that provided even further benefits. And we would also like to hear if any of these 6 is resonating with you. So if you can write in the comments or share during at the end of the presentation or now would be great. But otherwise, I'll pass the word to Hayden.
Yeah, thank you. Thank you, Mandy. And one thing I want to say just on this slide and also teeing up the subsequent ones is one way you can think about this is we've presented a really complicated view of 3D printing. We say you have to account for A, B, C, D, E, F, G, your full manufacturing process chain, your file formats, etc. The other way you can think about that is like what type of industries and what type of end use products can justify that much complexity. And the parts that you see on your screen are all really high performing goods in most cases, like hypersonic missile, or maybe not missile propulsion system components to football helmets for NFL athletes and so on. And so if you're in an OEM position where you're designing and producing products, thinking about things at that really complicated level is necessary. Over time, it becomes second nature in the same way that if you're running a water jet, like you don't worry about, oh, I need a DXF file. Like you just have that baked into your process and your workflow. And the same is true with 3D printing and additive manufacturing. But the lesson of now the subsequent slides, and I'm intentionally not going to skip ahead just yet, I'll do it in a second, is how can we make this easy? How can we build muscle memory and pick easy applications that make a lot of sense, not just at an OEM level, but at someone in the supply chain, a contract manufacturer, service bureau, job shop, whatever you call yourself, to build that muscle memory so that when you want to go and pursue more sophisticated, more complicated applications that have a longer process chain, you have a lot of familiarity and experience already to help avoid making some of the early mistakes that we've seen others in industry do. So one of the most powerful applications that came out a long time ago is the use of simple FDM 3D printers. And FDM just means when you Google 3D printer, that you usually see an FDM machine. It just means that you're extruding plastic filament through a nozzle and building your part that way. And one of the most simplest but powerful examples is using it for jigs and fixtures, alignment tools, things like that. If you were going to make, say, this tool on the bottom right, which is, for placing the decals on a Volkswagen car, if you're going to make this tool out of machining, or some other process, like it would be a pain. The stock material would be expensive. You'd have to do setup, you have to do the CAM programming, everything else. And in the additive context, all you have to do is do the design work for something simple like this. All you have to do is do the design work, take it to the machine, press print, measure it, and then go through a little bit of that iterative loop that Mandy talked about earlier. But we're reducing the number of process steps in this case and pursuing a fairly simplified application. The cost to make this part, like the cost of filament, is probably roughly commensurate to the cost of the hardware that you can see, like the bolts and so on. Like it's really inexpensive. This is less than $10 to produce internally. And the machine used to make it is itself only a couple $100. So, I mean, not these specific ones. The Ultimakers are like randomly somewhat expensive, but there are many machines like this that are pretty affordable, pretty easy to use, and we can of course give you some suggestions on where you might start. So this is often where folks start with 3D printing, is they say, I have opportunities on my shop floor to do a better job to improve repeatability of outcome or to make things easier for my operators. So often it's ergonomic applications where it doesn't make sense to like make this part out of milling or God forbid molding for quantity of one. But 3D printing can be a very powerful tool to make really low cost productivity enhancing components. Another example of this is from an electrochemical machining application where so if you're not familiar with ECM, you use like a mandrel. Basically, you flow a material and then a braid through electrical current, a base metal typically, to then form a shape. This is a really generic way to say it, but often like the rifling on a gun barrel, for example, would be made in this way, especially at the hobbyist level. They always do it that way. And so the process is governed by some kind of interesting dynamics, but it's mainly governed by the flow of that working fluid and how it interfaces with the part that is being machined. And so optimizing the design of that tool is really important. And often we're playing it with, very fine adjustments in geometry on the order of millimeters or maybe even less. And so this is an example from a research publication you can see in the top right, where they bought a machine that costs less than $200, printed, inspected a couple different versions of tool, and you can see in these three images here how they iterated a couple of times and then got a really, really good profile of cut, let's say, a finished outcome as a result of using really inexpensive tooling made by 3D printing. And so depending on your application, I often think of additive making the most sense at that job shop kind of shop floor level in tooling applications, in jigs, fixtures, etc., where you can build a lot of practice. So in order to make this part, and I actually don't have a photo of the tool itself, but you can conceive of it, right? Like it's usually a tube type shape. In the process of making that part, they would have gone through many of the steps that Mandy talked about, from optimizing the orientation during printing to learning how to design support structures and remove support structures to inspecting the part and correlating the geometry that they printed to their design intent to the outcome that they got, the one that's measured and shown on your screen. And all of that can be done in this case, right? We're talking about a $170 machine tool and like a $20 part. And then as you look to do more sophisticated uses of additive, well, you've already built out that practical experience. You sort of already know what you're doing because you've gone and you've done it a couple times before. So you can migrate to customer facing applications or applications where you're much more sensitive to outcome than in a simple kind of just getting started tooling universe. And actually, if you look at the part production in additive, you'll see that and this is on the left from a report called the Wohler's report. If you're in the additive industry and you're like MIT and you're teaching classes about it, you need to buy this report. But for you, I wouldn't. It's really expensive. I don't know if I would justify the $800 or whatever it is. But it just kind of summarizes the industry landscape, and you see that like almost half of all printed parts are used for just like engineering, fit and function testing, assembly, so on and so forth. And then down here a little bit at the 4% level, there's tooling applications as well, but these are often surveying large manufacturers or service bureaus. There are many folks that are not asking what they do with additive, and I think if you surveyed the whole world, tooling would be actually a larger percentage. But you can see that end use parts, so parts that are then being sold to customers either standalone or as part of assemblies, that is not the majority of printed parts. The overwhelming majority is for use cases where printing quantities of 1 or 5 or 10 low quantities is much more competitive, faster, easier than using the conventional manufacturing processes that we normally might use, like milling, turning, molding, et cetera, et cetera. So one question you ask yourself always is, if I want to get started with additive and I want to print at some volume, right? Not quantities of 1, but quantities of 1,000, 10,000, 100,000 or more. When do I make the decision to buy printers and do it myself? And how do I think about that decision versus when do I work with a contract manufacturer or service provider to help make those parts for me? And what I'm trying to do here, and I'll actually talk about the stuff on the screen in a second, but what I'm trying to do here is link this back to the point Mandy was making about the complicated process chain for certain types of production with additive. It takes a while to learn. And so let's imagine for a moment that you, for whatever reason, you're producing merchandise for MIT, I guess, because this is a model of the famous MIT dome. And at one point in time, some enterprising students disassembled a police car and put it on top. So maybe we got to get a Lego police car to put on top in the next slide. But let's assume for a moment you want to make this at some scale. You want to make 10,000 of these and sell them to MIT alumni or whatever, right? I don't think that's a great business, but let's assume you thought it was a good business and we did too. So what are your options available to you? Well, the first row here is saying, let's imagine you want to buy machines and print it yourself. How much is that going to cost you? And the answer is going to cost you a lot. And it's going to cost you a lot because the machines themselves can be expensive, depending on the type of machine architecture. The one that Mandy showed previously that spreads powder and uses a laser, those are often 6 figures. Like the entry level is about 100,000. There are some cheaper ones, but they're kind of scary, dangerous. But the entry level for that is about 100K, and then like a really good production machine with 4 lasers or 8 lasers or something like that can process a lot of material, right? Those might be $1 million or more. On top of that, you buy the equipment, the printer, you have to manage all those other workflow steps that Mandy was talking about. And you have to manage them both from the point of view of equipment. So you might need specialized heat treatment furnaces, you might need wire EDM, you might need certain types of chemical, like machining capabilities, complicated depowdering units, like the list goes on. Every one of those boxes often means a machine tool. But on top of it, your team needs to know what they're doing. Like they need to know how to work on those iterative loops between different process stages and design intent. in order to dial in each node in the process to get a good outcome. Because you can imagine, like, you and industry generally could and has spent a lot of time on trial and error iteration because they didn't quite know what they were doing. And they said, okay, things are going wrong at some step. Let me go back down the process chain, try to make some changes, reprint, remeasure, etc., until they get things right. And that can take a lot of time, a lot of cycles of learning, and ultimately a lot of pain as far as the money that you might spend. So I say that you have in your process confidence here is pretty low to get started, but it's fairly high risk because of the capex required to actually make this part at some scale. And you also on this far right column, like you probably have to add some people to the team or send some people to classes like the ones we teach, et cetera, in order to get them ready to work. Now let's assume for a moment you're going to use a service bureau or a contract manufacturer instead. So you're not going to buy equipment and you're going to work with the vendor. Well, then we can say that costs are reduced in many ways, right? The capex is not, you're not shelling out for capex. You don't need to bring in all that design competency in house, right? You're working with folks who have done this for a living. And so they've gone through all that pain and trial and error and so on for you and can translate that into success for your parts. And the process complexity is much lower because then you're just communicating like what your part requirements are. You're sending drawings and specs and those sort of things. And the contract manufacturer is then making it for you, or doing one step in a process chain, and you're working with the supply chain to do a few other process steps, like different ways to configure it. But ultimately, life is much easier. Now, the last step, we could say, what if we, instead of 3D printing this, we tried to make this a different way entirely, a way that we understand really well already. We tried to machine it. I know you wouldn't machine this particular geometry, but you want to mold it or cast it or whatever. Well, in that case, life is really good. Life is really easy, right? We already know what we're doing. We already have the equipment available. We're very confident in our staff and our organizational processes. We don't have to add anyone else to the team. Um, in this fictional example, the right way to make this part is definitely not to 3D print it either in option A, option B, but is actually just to keep doing what we're already doing. And so the question you want to ask yourself, the purpose of this slide is to say that there are some applications in the world. I'm actually going to jump back. There are some applications in the world, end use production applications, I mean, where having a really complicated, capital intensive process chain makes sense because you're making the highest performing goods in the market. And so if you're in aerospace or medical devices, or in some cases defense, additive just makes sense because it's the only way to make the good parts that customers want, nowadays. But if you're working in much more cost sensitive industries, like if you're making fasteners for a living, right, or whatever else, like consumer products, things that where you have a low margin, you don't care about device performance all that much. You care more about aesthetics, for example. Additive doesn't make a lot of sense. And that's an important realization that we've had, that the industry has had generally, is that additive is a tool in a toolbox. And there are use cases where it makes so much sense. It's the only technology, like for hypersonic propulsion. It's the only way you can make these shapes. So you have to print them. For other use cases, though, like printing simple MIT dome doohickeys, right? Additive is not the way to go. And if it is the way to go, it might not make sense for you to try to do everything yourself, but instead to build that muscle memory by working with experienced end users. And so that's kind of the end point of this slide, is to say, like, there's a few different approaches we've seen industry take. We've seen industry do the buy a printer and figure it out model, spend tens of millions of dollars on equipment and never get to a successful production use case. And then those companies look at 3D printing and they say, man, this technology doesn't work. We tried, we failed. And that's not necessarily the right takeaway. At the same time, other companies said, well, we think there's a way for us to use printing, but we know we're not the experts. We want to work with the experts. And there's a lot of benefits there to reducing risk and cost up front. There are also some drawbacks, though. And so it depends on, it really heavily depends on your company's own risk tolerance, your production goals, the sensitivity of your application, the volume of parts that you're printing. If you call up a contract manufacturer and say, "Hey, I want to make 5 of these, and they're going to cost, and I want to pay $300 a piece," like good luck. A lot of people are not going to be interested in that business. So things are always a little bit over more complicated than the way we share them. But anyways, the point I'm trying to make is that when you think about getting started with printing, don't try to shoot the moon in your first application. Start with things that are within reach, where the capital risk is something you can totally bear, totally tolerate, where you have people available who are interested and eager to learn, and so you can build that muscle memory with less cost, less risk, and then graduate your use cases as you go. And one way you can help de-risk that technology. Granted, it's not for production, it's for prototyping, is you can give us a call, and we would be very happy to work with you and enable you to access all the machine tools that we have available so you can get started and then build confidence and then maybe go buy your own machine or scale a part up into production with one of these contract manufacturers. So three takeaways for today. First is don't underestimate the influence of design. As Mandy was sharing, every step in your process chain, whether that's a really long process chain or a short process chain, is going at some point to be fed back into your CAD design. And so being very thoughtful and intentional and iterative with your CAD file is really important to getting right outcomes. Second is when you want to print something, make sure that printing makes sense. Don't just print just to print. And as you do graduate your use cases of printing, think about ways where you can introduce the technology at low cost and risk. Again, tooling, jigs, fixtures, prototypes, these are great places to start. Build that familiarity over time and then get more and more ambitious rather than starting with the most ambition possible. And then last is rely on your network. That network now includes us at MIT. You can always send us an email and we'll answer questions. It includes folks like MassMEP that I know have quite a lot of programs and opportunities to help you adopt 3D printing technology. At one point, they had like a 3D printing loaner program. I don't know if they still do, but you could get a machine on loan from them. And it also includes the service bureaus, contract manufacturers, 3D printing equipment manufacturers, though to a lesser extent than the other ones. And there's a ton of them in Massachusetts. Massachusetts is maybe the most dense state in the entire country for 3D printing expertise. So last, we say you should never stop learning. It's not just an MIT thing, that's a life thing, right? I consider myself a lifelong learner. And we do have some opportunities for you to do it. I mentioned I would put a few different plugs in here, so I'm sorry. This is the second plug. But we do have a class coming up from April 13th to 17th, where the whole goal is to work with you to try to design an application, build a business case, envision a production chain, so on and so forth for something that you might want to accomplish with 3D printing. So if that sounds interesting to you, you can take a look at the QR code and feel free to sign up. But I'm not going to like oversell this thing. The other, maybe more important stuff, the free resources, because that class does have a cost. There are many great resources available to you. You have, and we have some links to the left. Often I see a lot of great stuff on Additive on LinkedIn. And that's just a matter of like clicking follow on people that post interesting things and staying in the loop. We actually have a group. I didn't put the link here, but if you're interested, let us know. We have a group for alumni of our programs. That's mostly a jobs board. But if you're interested in a career in additive, we can share resources there. And then there's great journals, conferences, and trade shows. I mentioned Formnext, the one in Germany. If you don't want to go to Germany, the largest 3D printing trade show in North America will be in Boston this year, actually at the same dates that I have here, from April 13th to 17th. So it's low cost to go. If you can't afford it and you want a free pass to the expo, send us an email where we have a booth so we can just like give you those. That's fine. We're happy to do that. Go check it out because again, it's in your backyard. It costs you nothing other than travel, and you can see the whole industry, at a glance, and also get inspired by seeing what other folks are doing with printing technology and thinking about how you can do it yourself. Uh, that's it though for the lecture, the talking at you part. Just wrap up by saying if there's some resources that you're interested in. Like I said, on our website, you can find all of our machine tools if you want to take advantage of some of them. Even if you want to tour and just come look at them, take a look. And then, of course, you can always email myself and Mandy. Be very happy to answer questions. We now consider you our good friends, so don't be worried about bugging us with questions that might seem too small or too big. Uh, we're meant to be a resource, and you know that's that. Thank you.
That's perfect. Thank you so much, Hayden. Thank you, Mandy. That was incredible and very valuable information. Hayden, thank you for touching upon MassMEP's additive loaner program because that is still active with MassMEP. So if you're interested in getting your feet wet with a 3D printer and not looking to maybe go diving into the pool and purchasing a 3D printer yourself, if you want this to get your feet wet, we definitely have this program available to you. So after this call, I will be reaching out to each of you with some follow-up messages, with some contact information for them, the recording of the session, and then yeah, if you have any questions to MassMEP or to MIT, please feel free to reach out to us. Thank you all for joining us for part one of this series. We're looking forward to part two, and yeah, I'll be in touch with some confirmation emails as the dates gets closer. But thank you all for joining us this afternoon. We appreciate it. If
Yeah,
anyone
thank you.
has any, I'm sorry, Hayden. If anyone has any questions that they have that they don't really want to take during the recording of this session, we'll stay on for a couple minutes afterwards and answer any questions that you like. Thanks, everyone.
No, yeah, thank you. I was going to say the exact same thing. I was going to say we have another 11 minutes, and you know, in those 11 minutes, you can ask us anything you want. And maybe you know, one thing that might be helpful is just you can always say, hey, here's why I'm here. Here's why I'm thinking about 3D printing. Here's the type of parts that we make. You know, do you have any suggestions for us on how we think about the technology? Like you get ask anything you want. Um, and I'll be happy to share, and Mandy as well.
Perfect. Without further ado, thank you, everyone. Have a great rest of your day.
Hayden